Welcome to CEC lectures. Myself Dr. Preeti Jagmani. I am an associate professor from Department of Computer Science, Aryabhat College, University of Delhi. So in this series of advanced data structures and algorithm, today's topic is about Splay trees. So when I say Splay trees, that means I am talking about a particular data structure which is obviously in the form of trees. So trees, as you all are aware, are non-linear data structures, and Splay trees, as far as concerned, are actually altered version of binary search trees. Like binary search tree, all the operations including insertion, deletion and searching are supported by your Splay trees data structure, along with one extended operation which is known as splaying, and hence the name Splay trees. So these Splay trees are basically self-adjusted binary search tree data structure. That means these are in the form of search trees, they are binary trees, and also they are self-adjusting. So self-adjusting, let me help you recall, we have also covered this self-adjusting kind of nature of binary search trees in AVL trees. So AVL trees are also self-adjusting, or we can say self-balancing trees, which essentially means that the tree structure is adjusted dynamically on the basis of accessed or inserted element. When I am talking about self-adjusting binary search tree, that means these tree structures are adjusted automatically on the basis of the newly accessed or inserted elements. And if we talk about AVL trees, so AVL trees are basically self-balancing binary search trees. That means they balance themselves automatically, or we can say they themselves balance themselves dynamically. So self-balancing and self-adjusting, here is a thin line of difference between the two. So our Splay trees are actually self-adjusting binary search trees. That means it the one of the properties of this Splay trees is they automatically reorganizes themselves so that the frequently accessed or inserted elements become closer to the root node. I am repeating this line once again because this is what the bottom line, or this is what the main agenda behind this Splay trees. So these Splay trees are trees that automatically reorganizes itself so that frequently accessed or inserted elements becomes closer to the root node. Now what does it mean? I'll be covering this in a short while. Going into the history of this particular data structure, this was first introduced in 1985 by Daniel Dominic Salter and Robert Andre Tarjan. In 1985, these two computer scientists introduced this kind of trees. So basically these are having simple and efficient implementation, because everything except this splaying point is similar to that of binary search tree, and you all are aware that the implementation of binary search tree is simple as well as efficient also. And because of this simple and efficient implementation, the operations like search, insertion and deletion operation are performed in order log n if I am talking about binary search tree. To be very specific, in case of Splay trees, the search, insertion and deletion operations are performed, or they are going to take order log n time when measured in amortized terms, or I can say these trees allows to perform search, insertion and deletion operations in order log n amortized time complexity. Please notice here I am talking about amortized time complexity, not the asymptotic time complexity, where n obviously is the number of elements in the tree. That is the general definition of n. So nothing new here, but order log n for search, insertion and deletion is amortized time complexity for your Splay trees. Basic idea, as I was saying, that the most recently accessed or inserted element should be brought closer to the root of tree, and in order to bring that particular element which is recently either accessed or recently inserted to closer to the root of the tree, this can be done with the help of some rotations, or maybe it could be a single rotation or it could be a sequence of rotation, and these rotations or this operation is known as splaying, from which the data structure derived its name. So, splaying, when we look into the details, actually is a process of restructuring the whole tree. Now, how this whole tree is being restructured, though the agenda is we need to make the most recently accessed or inserted element the new root, or we can say kind of closer to the new root, and these elements are gradually moving the remaining nodes closer to the root as well. So, this is what your splaying process is, which is kind of a restructuring, and the agenda behind this restructuring is to move the recently accessed or inserted elements to the root of the tree. Now, why this, the first question which comes up in our mind is why this is required, why this splaying is kind of introduced along with the normal operations like search, insertion and deletion. So, basically we can say splaying is designed in order to optimize the access patterns in binary search trees. Now, what I am talking about is, let us try to understand this with the help of an example. I am sure you all are aware with the help of with the concept of cache memory. Now, this cache memory actually works on the principle of locality of reference, where frequently accessed items are likely to be accessed again soon. So, this principle of locality of reference is being leveraged. So, this locality of reference says frequently accessed nodes are likely to be accessed again soon, and thus your splaying is designed in order to optimize the access pattern, because you all are aware that in a particular tree structure the most accessible element is nothing but your root element. So, whatever element is recently searched, if I am bringing that particular element onto the root with the help of splaying, and I am doing this because of principle of locality of reference, or by leveraging the principle of locality of reference, and I am hoping that this particular element is likely to be accessed soon again. Now, why I am hoping so? Because my application says so. So, this splaying trees, splaying operation or splay trees are basically efficient for applications where frequently accessed data is likely to be accessed again soon. So, these type of applications are there in which splay trees are to be used. So, splay trees are not for any of the normal applications, but only for the applications where frequently accessed data is likely to be accessed again soon. And if we are going to do this splaying in some such manner, so what are the benefits we are going to reap by this splaying trees, or by this addition of an extended operation which is splaying? So, first is access time is improved. As I have told you, frequently accessed nodes come closer to the root, or most likely they also become root. So, splaying reduces the time it takes to find them in future searches, because the root, accessing the root of a particular tree is nothing but an order 1 operation. So, access time is obviously improved. Then they have the property of this self adjustment, or in they self balance themselves as well. So, splaying provides a form of self balancing for the tree, ensuring that it remains relatively shallow, especially for the frequently accessed nodes, and the height, being of a lesser height or being relatively shallow is going to give them we can say advantage of fast search, fast insertion and fast deletion also. So, this self balancing form or self adjusting thing ensures that the tree remains relatively shallow and the height should not be kind of skewed either on the one side or on the other side, especially for the frequently accessed nodes. As far as time complexity is concerned, I have just told you that we are going to calculate the amortized efficiency, not the asymptotic efficiency. Why? Amortized time complexity we adopt in those situations where a single operation can be expensive while the other operations are kind of we can say non-expensive. So, if we talk about the searching, if we talk about insertion and deletion, these are actually in case of binary search trees, these are we can say non-expensive operations, but when it introduces this self adjustment or when it introduces this splaying, this single splay operation might have a worst time complexity of order n, while the other operations are generally order of their height, and I have already told you that height is kind of shallow. So, while a single splay operation might have a worst case time complexity of order n, the amortized time complexity for a sequence of operation is going to be order log n. This means that the average time complexity, and average time complexity we measure with the help of amortized analysis. So, this means that the average time complexity for a sequence of operations is going to be logarithmic, which is considered as a reasonable we can say reasonable time complexity. So, basically how it is performing all these operations, let us see that with the help of an example. So, for instance, let us take a value a which is supposed to be inserted into a particular tree, and the tree is obviously the splay tree. So, if the tree is empty, the A is going to be the root of the tree and exit, because the newly inserted element is on the root. But if the tree is not empty, that means it is already having some elements. We will be using binary search insertion operation to insert the element, which says that first of all you need to look for the particular position of that element where the its appropriate position lies in case of this binary search tree. Then we insert the element, and that is not the end of the operation. After insertion of element, we will also perform splaying on the new node. That means we will try to keep this newly inserted node close to the root node, and this is not only after the insertion, but after searching an element in the splay tree, the node consisting of that element must be splayed as well. So, actually nodes are splayed. This is what the we can say correct terminology is. So, after searching of a particular element in the splay tree, the node which consists that elements must be splayed as well. So, after we can say insertion, after searching, splaying is to be performed. After deletion, there is no question of performing splaying, because that node or that element we can say is already deleted. So, yes, after searching and after insertion, splaying is to be performed. So, splaying, when we talk about in simpler terms, just a process to bring an operational node to the root, and this is done with the help of rotations. Now, what are the types of rotations? Now, please recall AVL trees in which we have gone through different types of rotations: left rotation, right rotation, then left rotation, right rotation, and so on and so forth. On the similar lines, your splay trees are having 6 types of rotations. What are these rotations types? Let us name them first, and then obviously we will be looking into the details of each and every type of rotation. So, the first one is zig rotation, then we have a zag rotation, then we have zig-zig, which is a zig performed and after a zig, then a zag-zag, which is a zag followed by a zag, then jig-zag, which is a jig followed by a zag, and converse of it, which is a zag followed by a zig. So, these type of 6 rotations, 6 types of rotations are available with splay trees: zig rotation, zag rotation, zig-zig, zag-zag, zig-zag and zag-zig rotations. Now, splay trees, when we talk about in terms of efficiency, they are highly efficient because of this self-adjusting nature. Because of this self-adjusting nature, what is the improvement which we are going to get? This actually reduces the overall access time for the frequently accessed elements, because now those elements are available either on the root or kind of close to the root. So, because of this property of efficiency, these splay trees are a good choice for the applications that require fast and dynamic data structures, such as caching systems. So, caching is completely based on the principle of locality of reference. So, hence for caching system, splay tree is the best choice, or maybe for data compression, they are the good or appropriate choices, and also for the network routing algorithm. Although these splay trees do not guarantee a balanced tree structure, as I have already told you in in the inception of the lecture, that here is a line of difference between balanced and self adjusting. So, they are self adjusting trees, but they do not guarantee a balanced tree structure, and here is what is the other side of the coin, which may lead the performance degradation in worst case scenarios. Also, splay trees are not suitable for the applications that required guaranteed worst case performance, such as any real time systems, or maybe any systems which is critical on safety issues. All those systems require guaranteed worst case performance. In all those situations, splay trees are not suitable for all those applications. So, the bottom line is on which your splay tree is relying is that each time an element is accessed, it is moved to the root of the tree, creating a more adjusted, I can say, not balanced in terms of height. Obviously, even if I am using the term balanced, not in terms of height. So, creating a more balanced structure for the subsequent accesses. So, this is what I can say is the key key element or the key feature of a splay tree. Now, when we talk about how this splaying is done, as I have told you, there are various types of rotations. These rotations, you can say, are actually nothing but kind of local transformations of the tree, which are going to change the shape of the tree, but preserve the order of the element. Preservation of ordering of elements is obviously necessary, because we are talking about a search tree. So, we cannot we can say we cannot or we should not disturb the order of the elements. So, order of the element is to be preserved, but yes, the shape can be kind of changed with the help of local transformations, and these local transformations are nothing but we can say the rotations, and splay trees are characterized by use of these rotations. Rotations are used to bring the accessed element to the root of the tree, and these rotations can also in some cases can also rebalance the tree if it becomes unbalanced after multiple accesses. So, when we say we have seen the applications which are suitable for splaying, we have also looked into one or the two scenarios which are not suitable for splaying trees. So, what is the scenario, or which is the scenario in which your splaying is going to help? So, for example, if a node n on the access path is at depth d before the splay, after splay it is going to be at the depth d by 2, that means half of the depth of that tree, while root is the exception of this particular we can say rule, or this particular feature. Exceptions are the root, the child of the root, and maybe the node is played. Overall, the nodes which are below the nodes on the access path tend to move closer to the root, and splaying gets amortized performance. That amortized is nothing but order. Amortized performance, or the measurement of that amortized performance, is order log n, and amortized analysis is done in those scenarios in which one particular operation is expensive while others are not expensive. So, when we talk about in a comprehensive manner that what are the operations in the splay tree, so operations can be search, insertion, deletion and splaying. So, insertion, as you all are aware that we need to insert a new element into the tree. For inserting a new element into the tree, first of all its position, its appropriate position is to be determined by using the normal or the regular binary search, binary search tree, we can say searching, and then finally it is inserted, and then we need to apply the rotations in order to bring the newly inserted elements to the root of the tree. Now, any of the rotations among those lists which we have just considered, zig, zag and so on and so forth, those rotations are to be applied. When it comes to deletion, so to delete an element from the tree, we need to locate it using binary search tree search. Then if the element has no children, we simply remove it. This is what a standard procedure, and this is what we have seen in our we can say binary search tree data structure also. If it has one child, promote the child to its position in the tree. The most complicated case is the element or the node which you want to delete is having two children. So, in that situation, if it has two children, find the successor of the element which is, we can say, the smallest elements in its right subtree, swap its key with the element to be deleted, and then you delete the successor instead. So, that is kind of a standard procedure which is done with the help which is done when we perform the operations in binary search tree. And search, as far as concerned, is again a simple, a very a well known operation in case of a BST, which is we want to search for an element in the tree. We start by performing, or we start by searching it from the root. If the element is found at the root, we are done with it. If it is not, if the element which we are looking for is lesser than the root or is smaller than the root, we will look into the left subtree or we will look into the right subtree. But in case of a splay tree, if the element is found, we need to apply rotations to bring it to the root of the tree. So, it is not just searching and we can say reporting about the we can say position. It is also the applying rotation to bring it to the root of the tree, and if it is not found, we need to apply rotations to the last visited in the search, which will becomes the new row, which will become the new root. Now, this is important. If the element is not found, we need to apply rotations to the last node visited in the search, because that is the recently accessed node now, and then hence because of those splaying thing or because of those rotations, the last node visited in the search will becomes the new root. So, if we talk about what we have covered in this particular lecture, So we have started with with a new data structure which is Splay Trees, and within this Splay Trees we looked into what is splaying, why these kind of trees are given such name, then what are the operations, how these operations are being performed, what are the scenarios in which these Splay trees are actually we can say important, or should be used, or they are most appropriate, we can say, or what are the scenarios, what are the applications in which Splay trees are not the appropriate or not a reasonable choice. So, we have covered the basic of all Splay trees. In our upcoming lecture, we will be looking into all type of rotations which we have just named here in this lecture. Here is a list of references which is being used for the preparation. I hope you have enjoyed this lecture. I will see you in the next. Till then, take care. Goodbye.